things on track. So welcome to the first session of talks for FHPC. I'm pleased to introduce Christian Harrington, who's going to be telling us about using functional programming in a real application that matters to all of us who hope to retire.
Okay, so hello, my name is Christian Harrington. I'm a student at the IT University of Copenhagen. And this presentation is based on work I've done together with Peter Sestoft and David Christensen, who are both here today, and Nikolai Dahl, who sadly couldn't be here today. It's part of the Actuarial project, which is a joint effort by the IT University of Copenhagen, the Copenhagen University, and Idlund, which is a Danish insurance company. The goal of the Actuarial project is to produce a new generation of software for the life insurance and pension industry, and it's supported by funding by the Danish National Advanced Technology Foundation. Okay, so I'm going to talk about how we would like to write something like this instead of something like this. This is a whole bunch of CUDA C code. But before I get into details, once I got the main motivations for this, for the Actuarial project, we would like to be able to implement more accurate modeling of life insurance and pension products. One of the ways this is being addressed is through the Actuarial modeling language, which David has been working on. It's a functional, statically typed, domain-specific language to describe various pension products. The Actuarial project is also motivated by the Solvency II EU directive, which is a response to the 2008 financial crisis. It includes many mandates for insurance companies, and there's one in particular that's relevant to what we've been working with, which states that insurance companies must ensure that ruin occurs no more often than once in every 200 cases. But what this means is that insurance companies must be able to show that in 99.5% of future eventualities they'll be able to pay what they owe to their customers. Because if not, then they go bankrupt, which is bad for everyone. Okay, so unfortunately there's going to be a lot of actuarial terms, and I'll try to go through them quickly, but during actuaries here, I'm sorry, I'm going to be kind of fast and loose with the terms. So the most simple thing is a customer. A customer holds a policy which consists of one or more life insurance or pension products, and I'm very pleased about this. So then for an insurance company, they then have a portfolio which consists of many customers, each holding policy with one or more products. So I've said product a few times. I'm just going to go over what I actually mean when I say that. But first, to model products, we use state models. So this consists of usually at least two states, and some transitions between these states, along with some transition intensities. So as an example, these states could be alive and dead, and this is a very simple insurance product. This is specified in AML, and what this says is that the insurance company is obligated to pay $1, so it's not a great policy, when the customer transitions from alive to dead, given that the insured is under some age. Could be if he's under 65 and he dies, the insurance company pays him, or more likely his family, some amount of money. So I said cases and future scenarios before, and this can include many things. For example, changing life expectancies and things like that. But we're only going to be looking at one thing today, and that's the interest rate path. So an interest rate path is simply how we think the interest rate might change over time. And we cannot predict this, so we have to make some guesses and look at a lot of different possible interest rate paths. So for here, at time 0, the interest rate might be 3.5, and then point 1 is 3.7, and it drops and changes over time. So what we're calculating is reserves, and this is defined as the expected net present value of the future payments in a product, taking interest rates and transitions into account. So what this means is this is the amount of money the insurance company must have at some time to be able to pay their obligations. And it's found by solving Thiele's differential equation, which I won't be explaining, it's beyond the scope of this, but just know it's a differential equation, or a system of differential equations in this case. It might be easier to visualize it here. So the reserve changes over time. And what the intuition is that at the age of 30, this is the same product as before, which says that at the age of 65, if the person dies before that, they're paid some amount of money. But when the person is 30 years old, there's not that high of a chance of them dying, so they don't have to hold much of a reserve. But as time progresses, the chance of them dying increases until at some point, which means they have to have more money to be able to pay out their obligations. But at some point, it drops again, because once you've gotten to this point, there's a good chance you'll get to 65. So, if you remember the EU directive before, it says they have to show that they won't go bankrupt. So this means they have to be able to cover their reserves. That means that we have to find a reserve for each product, for each customer, for each different scenario. So this means that we are going to have to be solving a lot of differential equations. To do this, we wrote CLIRE. It's a CUDA-C program, and how it works is it simulates some amount of interest rate paths, and then it finds the it solves Thiele's for each product, for each customer, for each of these interest rate paths. So it's a lot of calculations, and it's very well suited for running on graphics cards. I'll start with some benchmarks. We wrote a version that also runs on regular multi-core CPU, so we'd have something to compare against, but it should be noted that we spend more time optimizing the GPU version. But we feel this is pretty fast when we compare it to other reference implementations, the CPU version. So that's a pretty big performance increase. And so you say we can do 10 times as many customers, and it's still faster than the CPU version. I was asked to include a bar graph, but it's not very kind of hard to see. And so you know that in this specific test, the CPU is a quad-core modern Intel processor, and the GPU we used was a Tesla C2075. And with more benchmark numbers in the paper. Yeah?
Is the CPU version vectorized as well as multi-threaded?
I'm not sure.
It's not.
It's not. Right. So I want to talk about one of the, we performed several optimizations on the GPU version, but I'm just going to be talking about one now. The way it works is we iterate through customers, and then for each customer we find the reserve for each interest rate path. And in our implementation, interest rate path is just an array of floats. So for each, so we have several or many of these arrays of floats. Now each the execution flow is determined by the customer's product. So the reason we do this is then we can we know a customer with a product has the same product as himself. So by bundling them by a customer with a specific product, we know there won't be much branch divergence because it's the exact same calculations we're using. So the execution looks something like this. And you might already be able to see the problem because it's the same customer but different interest rate paths. We have to read a lot of different places in memory, and this turns out to be slow. So what we did here was we interleaved interest rate paths so that for the interest rates for time 0 across all the interest rate paths are stored consecutively. So first we have all the interest rates for time 0, then all the interest rates for time 1, and so on. And because of this, then the execution looks like that instead. We can read chunks of interest rate paths from the global memory at once. And this meant a huge performance increase. But as you can see from this kind of optimization, it's hard working with CUDA C. And it's very low level, and you have to think about stuff like this, how stuff is laid out in memory. So what we'd like to do, instead of having programmers write this very complicated code, we like to generate the code. This is where the functional part comes in, because I mentioned it very briefly before, but we have the AML language, which is a much more high-level way of working with insurance products. So we'd like to take products specified in AML and based on this generate high-performance code for running calculations on them. And the dream is that actuaries themselves, who do not have much program experience, can actually work with AML, and this means they can test out new pension products, they can run the reserve calculations for the entire portfolio, and they can see how it affects the bottom line. So to do this, we've written another program called the Actuarial Calculation Processor, and it's written in Scala. The reason it's written in Scala is the original implementation of, or the first implementation of AML we used was implemented as a DSL in Scala, so it's easy to integrate. But what it does is it transforms some products into our internal representation of differential equations, and then based on this we can generate different code to perform calculations. So we've tried to write it in a modular way, so we have different code generators, and one of them is the CUDA code generator that integrates with CLIRE. So we have an embedded version of CUDA C, and then we can transform products into ODET representation to our CUDA C representation. Once we have this, we can print it out to a file and then use the regular NVIDIA CUDA compiler to get our CUDA code. It also gives us a central place to perform optimizations, because I mentioned we could have different states. Often the deaf state isn't very interesting because the person is dead, so not much happens. So you can often actually optimize that state out, which can also give some performance improvements. So this is the pipeline we've built. With ACP, we read customers in from some place. We read product specifications in. Then we link customers to our internal representations of products, and then we bundle this to a portfolio, which we hand off to a generator that then can generate code and execute it. And then we can get the results. So what we've done in practice is we've written a CUDA generator and a C generator, and a CUDA executor and a C executor. There's one very, very important part that's missing at the moment, and that's actually the AML component. We can't actually read in AML yet because it has been changing a lot, and we don't have, we haven't been able to keep up to date with it. So currently, all the products that we work with are hard-coded in with our internal representation. But the idea is to be able to read AML in. But the thing is, we still aren't quite fast enough, because we want to support that actuaries can sit and play with these, sit and play with the products, and waiting 11 minutes is still kind of a drag. The other problem is it's not really feasible for insurance companies to host a huge server with a whole bunch of graphics cards in. So we also experiment with cloud computing. This is where the name pays off. It's very preliminary. We don't have any hard results from it yet. We've integrated with Amazon Web Services, and the cool thing is you don't actually have to have a whole bunch of graphics cards sitting around not doing anything half the time, and you can spin them up when you need them. And it turned out it was pretty easy to parallelize across these machines as well, because you can just cut the portfolio into chunks and send them to different machines, and then put the pieces together again afterwards. But there's still a lot of future work to do. We'd like to get the AML integration working again. Like we said, it worked in a much earlier version, but that might be some significant amount of work. We'd also like to look at different solvers for solving Thiele's differential equation. Currently, we use the Boolean-Kuta for method, which is what's called which is not an adaptive step size solver, which means it always uses like the same resolution when solving these equations, even when it's not needed. We'd like to look at some adaptive step size solvers, which might be able to give us some huge or some large performance increases. But we're slightly worried that will affect branch divergence if different solutions result in different step sizes. Currently, we also only support pretty simple pension or insurance products that only have they only affect one person, but that different compound products where the obligations can be affected by multiple people, and they require some of these may require specialized solvers. We've looked a bit at it, but there's still a lot to do, and the work we have done is not integrated into the work we have done yet. So we've shown how you can use GPU and to some extent cloud computing to achieve high performance on calculations for pension and life insurance. We've shown how you can generate CUDA C code in a modular way based on some higher level representation. Thank you.
We've got plenty of time for questions.
Okay, so thanks. This was a great talk. This is a very neat thing to be able to do. If you could go back one slide to the future work thing. Oh, 2 slides. Yeah. So you say that you are thinking about experimenting with other differential equation solvers.
Yeah.
Is that something? I mean, I've heard of commercial SAT solvers. I assume there are commercial differential equation solvers out there as well. And then you mentioned earlier that that it's not feasible from a financial point of view for insurance companies to have big servers standing around. Would it be feasible to have to pay for a commercial differential equation solver? I mean, it's not something you've given much thought about, but
no.
Is it something that...
well, the thing is, most insurance companies do have some money.
Yeah, sure.
but I have no idea about the internal, like how that stuff works. So
no, but I mean, it's like every time if we wanted to use, I'm sure you could integrate some sort of commercial solver into this stuff. But then your customer would then have to have the user would have to pay a license fee to some other company, and
Peter might.
Right, yeah. So I'm Peter Sestoft, one of the co-authors. Yes, surely the insurance companies could afford a commercial solver, but actually there isn't much in this realm that's better than what we're doing for GPUs. Actually, the problem is quite simple, and which is a great thing for GPUs.
Oh, okay.
And I think actually maybe adaptive step solvers is actually not really useful anyway because of the thread divergence, which is a problem in GPUs, and because there are lots of discontinuities in these problems determined by these age cutoffs before 65 something, after 65 something else. So which means that the adaptive step solvers even have to stop quite often, and they don't really work very well in that case.
You can get that.
Oh, sorry. it looks like you have a setup where you have you can easily decompose the problem into portfolios. Portfolios. In this case, they're called customer-specific products. So they're independently valued, right? Calculated. So can you think of actually writing this down as a map overall, and then that's the level of parallelism you have, right? So that's what you use parallel, and then you have sequential execution of the valuation for each.
Yeah.
So would this fit into like a framework like Accelerate to express this at that level? And could you have you tried to experiment with that?
I haven't looked at that at all. I'm sorry, but it sounds interesting. Yes.
So this AML language is yours, you've written it, or is it from somewhere else?
It's written as part of the Actuarial project. Actually, you're sitting right next to David, who has worked a lot on it. So if you have any specific questions about that, I will direct you to him.
Do you do any compression of customers? So customers who have identical policies and very similar birth dates, do you try and compress them into one product?
We haven't looked at that, but we talked a bit about it. But the thing is that we just talked about birth dates, but it can be more stuff than that affects the insurance policy. It's also often that gender and stuff like that, so it can be hard to find two very close matches. But if you can find someone who has the same or very similar data, there's no reason you shouldn't be able to do that.
So how fast do we really need to be? If it's 100,000 customers, take a couple of minutes, maybe they can run to a weekend.
Yeah, but it's okay for doing like long-term planning. It's fine to do it at this speed, but we'd like to support that people working with it on a day-to-day basis actually have a way to experiment with different setups and see how it affects stuff.
You almost want to get to the point where you can move a slider.
Yeah, that would be
But for that
perfect.
you can sample the population of the customers.
Sorry?
For that you can sample the population of your customers and do the estimation of that.
If I may slip in a question about the business model, I was curious, the Amazon HPC instances that host the GPUs, is there a security policy such that an insurance company would put customer data on there, or?
Luckily I'm on the so I don't have to think about that. But that's a big concern because that stuff is really complicated, and I think most. Oh, sorry.
But actually, so a couple of years ago, the company asked me whether they should start using cloud, and I advised against it for security reasons. But it turns out that this company's customers, which are the insurance companies, are happy to use the cloud, and the Danish data protection agency and so on apparently are also quite calm about this. So they're actually using Microsoft Azure Cloud. So I'm not really comfortable.
We have some about that. We have some partners in the pharmaceutical setting, and they actually trust the cloud companies more security-wise than the HPC clusters organizations. So it has more to do with physical security, etc. That's mostly lacking in the true HPC sort of installations. So.
Well, let's thank our speaker one more time.